I see that the equation disappeared. So let me just rewrite the action. So we had some, what was it? F prime of phi divided by omega squared r bar plus 6 Okay, so this is what we reached, and we said the following, that we are going to consider this to be 1. So I'm going to assume that we have this relation. This will simplify the equations because I have freedom to choose omega as I wish. And so actually what it gives is that now we are going to get some dynamics. For example, what is this term here? Let me just write just this term. This term is g mu bar d mu omega d mu omega. But omega is this. Is what I have. Each one, I just need to make the derivative of this. So it's just d mu f prime divided by the square root, d nu f prime divided by the square root. And this term here, is just the second derivative of phi times d mu phi divided by twice the derivative. And this is the same. So I ended with this relation, that this is equal to f double prime of phi squared divided by 4 times f prime of phi times the kinetic term for the scalar field.
Derivative of phi with respect to mu and mu, what are saying?
The derivative respect to mu,
Mu of phi.
yes, it's just the index which is changing. So this is what it means. Okay, so you have this term. You do the same thing with this term. That there is nothing really complicated about this part. So you just do the calculations, and then at you end with something which is the following. You get that this is equal to C4 divided by 16 pi g minus g bar, and I have r bar and minus 3/2 f double prime phi squared divided by f prime phi squared the kinetic term. I should write it like this. and minus the potential. The potential V phi is the potential we had before divided by omega 4. So it's just this. So now we have really actually something which is GR plus a scalar field which has a kinetic term and a potential. So it has dynamics, so it is a degree of freedom. Because if it doesn't have dynamics, it is not a degree of freedom. It's not just a constant which is in the theory. It's really a field. So this, the claim, is that this is equivalent to the F of R theory that we had at the beginning. They don't look at all the same, but they describe exactly the same theory. If you choose some F of R, this is where things will appear here, and also in the potential, and that's it. But this is going to describe exactly the same physics. It's exactly the same theory. So the next step, which is pretty important, is this one. I didn't talk about that, the matter part. And this is going to be critical in the interpretation I will give later on about why these two frames are equivalent. The action part, the matter part, let us say that we have some matter fields. These are the matter fields. It can describe fermions, bosons, whatever theory you want to consider. You just add some fields there, Dirac fields, whatever field you want to consider. So I just write it collectively as psi of m. It's not a scalar. It can be any field that you can consider. This is always coupled to the geometry, the scalar field. So there is always some geometry there. If you take the, I don't know, the electromagnetic field, when you write the electromagnetic field, the action, you have minus 1/4 F mu nu, where F mu nu is just the d mu a nu minus d nu mu. How did you put these indices up? By using the metric. You say that it's g mu alpha, g nu beta, f alpha beta. So the metric appears here. So when you describe the matter sector, the metric is always there. So the action for matter is the matter fields and the metric. It is always there. So the point, the full point, is that we change the metric. So we change that metric here. So actually it becomes the metric g mu nu. I don't have it anymore. It's omega minus 2. And omega minus 2 is 1 over f prime. But let me write it omega minus 2. Now, because we write it with the new metric, the scalar field appears here. So what does it mean is that matter is coupled to that scalar field. So that is the crucial thing. And this is the modification of gravity. When we have first GR, we define some geodesics, and the matter is following this geodesics. Now I'm modifying gravity. It means that I'm modifying these geodesics. The path will not be the same. So I can write it as Einstein theory, so I will have the same geodesics, but because matter is coupled to that scalar field, the matter will feel an additional force which comes from this scalar field, which will produce a deviation, and that is equivalent to the other picture where I was saying that the geodesics are going to be different. I will write it as what we call a fifth force. But the crucial thing is that when you do this transformation, this rescaling, is to take into account that now the matter field is coupled to the scalar field. It's not coupled only to the geometry. So this is called the Jordan frame, the Einstein frame, sorry. So now let me answer the question, because now we have the full picture. So we said that we start with a universe which is expanding. That universe is expanding, and we can observe something which is called a redshift. But what does it mean that we observe redshift? Of course, I have no idea what was the wavelength of this photon which has been emitted by some star far away from us. I've never been there to check it. What I do is that I receive some photon, I measure its wavelength, and I go in a lab here on Earth, I do an experiment, and I compare to that. And I see that the wavelength has changed compared to what I have in a lab. That is my reference. I always need a reference to make a comparison. And then I say my wavelength is now bigger or shorter, etc. But I need a reference. And the reference is a lab. So when I make this comparison, I say, okay, it has been stretched, and I call this redshift. Now, in the second case, you do the conformal transformation, and you get Minkowski spacetime. In Minkowski, there is no expansion, so we should not observe redshift. But the point is, yes, we are going to observe also redshift. We should observe the same thing. The reason is the following, is that now matter is coupled to the scalar field in this new frame. There is no expansion, but matter is coupled to the scalar field. So what does it mean? Imagine that you have some matter field which has some mass. The mass is coupled to the scalar field, and that scalar field changes over the time. It changes with time. So now the mass of the field changes in time also. So if I take, for example, an electron, and an electron makes a transition from a state 2s to one state 1s. It makes a transition and emits a photon. The mass of the electron 1 billion years ago was different than the mass today. And we know that this distance here is proportional to the mass of the electron. So actually, that distance changed. So what's happening is that when the photon was emitted, that was the distance between the two states. We get a photon with a very small energy. The photon comes to us, there is no expansion at all, and we receive it with exactly the same energy, with this energy. Now we go to a lab and we do an experiment, and because now the mass has changed of the electron, in a lab it will be much bigger, and we get a photon with much bigger energy. And we are going to say, if we compare to that, clearly the photon lost some energy in the process. But actually, it didn't lose any energy. It's just a way of seeing that when we compare to the reference. And we say, oh, it lost some energy, so we call this redshift. So the main thing is the comparison to the reference. And in the first picture, we have expansion, and the expansion produces redshift. In the second picture is the coupling to matter. The mass of the particles is changing, and this gives the idea that there is a redshift. But, so in terms of, we can say one is universe is expanding, one is masses are changing, and it's normal because we are rescaling things. If I rescale a distance, this 1 meter, I call this 1 meter, I rescale all parameters, also mass. What was 1 kg, I rescale that to now this is 1 kg. So I rescale all parameters. So I'm rescaling also notions of masses, etc. And when we have to make an interpretation, I have to take into account everything. So this is why interpretation in this frame is not easy, because we have to take into account that it is coupled to a field, so the masses are changing, etc. So very often we say that mathematics is easier in this because I have a much simpler action, can do calculations in a much easier way. But the interpretation, better to go back to the first picture, because then I just say there is expansion, redshift, it's easy. The other one, I have to take into account many other things, etc. So that's the idea. So the coupling to matter here is crucial. Yeah? Questions?
I also see.
Yes.
So, is it like that in the Jordan frame we cannot comment about the degrees of freedom because it's apparently redundant, but it is hidden there, but we cannot see. So how will we sure that there is a real physical degrees of freedom unless I go to the Einstein?
You can do it directly in the Einstein frame and count the degrees of freedom. As I said, the only way to do it properly is Hamiltonian formalism. And people did it, and you get 3 degrees of freedom.
See, in there also.
Yes, in f of r directly, in the Einstein frame, in Jordan frame, sorry. Directly, and you get 3 degrees of freedom. So you don't change at all anything. You can interpret it here. The degrees of freedom are fine because even if it couples to matter or not, that doesn't change the counting. It changes the interpretation. But counting the degrees of freedom, that's okay. That you will get always the same thing.
So here, just I have missed one point.
Yes.
Like, a metal part of action, you are taking psi m is a metal field, and also you are taking G mu nu.
Mm-hmm. Yeah. No, what I'm saying is that the matter is always coupled to the geometry.
Yeah, that's right.
Always. And the example I took is the electromagnetic field, which has this form, but it has 2 indices which are up, and to put up the indices I had to use metric. So in any actually theory, when I put matter, matter has always the metric inside actually. So yeah, these they always come together.
And what you are telling just now about Minkowski, that if we transform the Minkowski means that line element
Yes.
with conformal transformation,
Mm-hmm.
then we observe the expansion.
Mm-hmm.
But that is only due to the metal part.
Mm-hmm.
Because this gamma omega is related with phi.
Yes.
So we are observing expansion.
Yes. I mean, we don't observe expansion.
No, means in metric means.
Yeah. Yes. But just to be sure about this point is that we never observe inflation or expansion. Sorry. What we observe is just things like redshift, for example.
Yeah, that's right.
So this is why, in terms of interpretation, I always have to go back to the observables. What do I observe really? Then after that, it's just matter of taste. If I want to say that the universe is expanding, then it's fine. It makes life easier. If I don't like this, I can say the universe is static. It's not expanding. But the cost is that I have to say that the masses of all particles is rescaled over time. So the mass of a proton today is not the same than the mass of the proton in the past. And all the masses in the universe, they get scaled in the same way with the same factor. If I want to deal with that, it's okay. To live with that, it's okay. Then after that, it's just a matter of how I like to look at it. The mathematics will be equivalent. The physics at the end, we have always to go back to what do I observe really. And to that, when you go back to that, you find exactly the same thing. We never observe expansion. We never observe most of the things. I never observe a gravitation field. I just observe the effects of that.
Effect of it.
Yeah. Like orbits and things like that. So when we go back to what we observe, it should be always the same.
Sir, as we have seen here, in both of the frame, in one frame, there is no expansion.
Mhm.
In one frame, we observe the expansion.
Mm-hmm.
Is it possible that we are, in some frame, we are observing the acceleration, but actually there is no acceleration? Due
No.
to the some the transformations we have applied, we are getting the acceleration.
Mm-hmm. No, there are 2 things. One is from the mathematics. The other one is physics. Is directly observations. The acceleration, we get it directly from observations. So we know that there is acceleration. Now, in terms of mathematics, if you work in the first frame, the interpretation is trivial. There is no problem. If there you get acceleration, means that there is acceleration. In the other frame, then it's a bit more tricky. If you get acceleration in the other frame, it doesn't mean that there is necessarily acceleration. But I remember some people published a paper saying that maybe we can even get rid of the initial singularity by changing frame. It's saying that maybe the singularity comes only in a specific frame. If I change frame, I can lose it. No, it doesn't work like that. The physics is the same. If I get singularity in the first one, I'm sure that this is a real singularity. If in the other frame there is no singularity, maybe we have to look more carefully to the matter sector, but it should be there somewhere. It's just hidden, like the expansion. It's hidden somewhere, but it should be there. So so that was on the interpretation, and let me just try to advance a bit more. What we do now is the last part of it is just to write things even more close to what we did, close to the standard picture we have, is that, as you can see, this is not a standard kinetic term. Usually we have 1/2 and a kinetic term. So this is called the canonical form. So we want to write it in a canonical form, and this is trivial. We just need to redefine the scalar field, and that's okay. So if I define my scalar field psi, I will define a new scalar field psi. It's not the matter field. It's just another scalar field. And I write it as square root of 3, the log of f prime of phi. Then actually, this 3 f double prime phi square root f prime phi square root times this is just
we are getting the new and new transformations everywhere. This is why we are getting from the hit and trial method directly, or we have to follow some specific rules. Hit and trial, and we are taking this is 1, 2nd, 3rd, and which one is the best, we are taking that one.
No, what we did so far, we have done nothing random. The first transformation, conformal transformation, was specifically to kill the coupling that we had to the curvature. So we didn't have any choice. So we had to do that. Now I'm doing the only transformation which is going to write all this ugly term here as 1/2 kinetic term. Because I want to write it in a canonical form, because this is the scalar field I know. I don't know when it is so complicated here. This is a structure which I don't know very well. So I'm trying to go back to the picture I know.
So I'm asking how we will go to this transformation, log this one. We are not going in the first step now. How we will know that we have to apply this transformation only?
No.
3 log.
No, it's okay. So
Log, yeah.
let's suppose we assume that, and I will just show what is the derivative here.
Because derivative is
Do you agree on that?
Yeah.
So then this term here, which is just the square root of this, is 3 times f double prime squared, f prime squared, and this, which is what I want here. So, so you just work it out. If you don't know exactly what it is, you write that psi is some function of phi, and you do the calculations. So you do that d mu psi is g prime of phi d mu phi. So the kinetic term here will be g prime squared d phi squared, and then you identify this with this, and you get what is G. Yeah.
It's the reverse engineering. You want this, so you will find a term from that.
So with this, I'm getting the last thing. Now I have minus 1/2, a standard kinetic term, minus some potential here, plus the matter, which is coupled to omega minus 2 times G nu, which means the omega is f prime minus 2, so it gives an exponential, which is exponential minus psi okay. So this is my final action. Okay, so the f of r theory I was talking about before is equal to GR plus what we call a quintessence field, just a standard kinetic term and the potential, and the coupling to matter, which comes in this way with an exponential.
So your question remains that in one frame, if we take transformation, we observe something. If we don't take, we don't observe something. Or then where to, one has to stop, or how we can conclude that this is the right picture.
The picture is in the both frames because they are equivalent physically. I don't change anything physically. Now the only thing is that in this frame things are a bit more complicated for interpretation because I have to take into account the coupling to matter. So then it's a bit more tricky. I have to remember that the masses are also scaled, the distances are scaled, that everything is scaled. Why there was no expansion? Because in one frame, universe is expanding. In the other frame, what I call 1 meter is changing over time. So actually, I have the feeling with my new scale, which is changing over time, that the universe is not expanding. Because every day I take 1 meter, which is bigger. So the universe is expanding, but the frame also. So at the end, I had the feeling that the universe is static, that it's not expanding. But it's just because I changed the frame. So at the end of the day, I have to take into account everything and also this part. Now, if I want an interpretation which is easy, I go back to the other frame because then I don't have the coupling to matter. Then it becomes simple, the interpretation. But both should give exactly the same interpretation. It's the same physics. There is no difference at all. The actions, they look different, but it's exactly the same physics. I don't change anything. Then if I say, oh, it's because the universe is expanding, or I say because the masses are expanding, then it's a matter of interpretation. But what I observe will be the same. Now that we have the first structure, let me go a bit faster. In the sense that, okay, so f of r is equivalent to that. As you can see, this is a general coupling. Whatever my f of r theory, it's always the same thing. It does not depend at all on the parameters. It's just some minus half square root of 3. This is very general. The kinetic term is also very general. It doesn't change at all. The only term which keeps the information of the initial f of r theory I'm taking is the potential. The potential has the information of my f of r theory. So let me rewrite the potential. The potential is the following. The potential was something like that. it's phi f prime of phi minus f of phi divided by f prime of phi squared, with the condition that psi is equal to square root of 3 log of f prime. So this is my thing. So let me take a simple example, the StarWitzke model. So for the StarWitzke model, f of r is equal to r plus alpha r squared. So I want to calculate that. So psi is equal to square root of 3 log of f prime of phi, so 1 plus 2 alpha phi, which means that phi is equal to exponential psi divided by square root of 3, and there is a minus 1, everything divided by 2 alpha. For this specific model, this is what I have. So, and the potential is just phi f prime minus f of phi divided by phi prime phi squared. So I replace phi by what it is. It's phi. F prime is 1 plus 2 alpha phi minus phi plus alpha phi squared divided by 1 plus 2 alpha phi squared. The phi they disappear. 2 alpha phi squared minus alpha phi squared is alpha phi squared divided by this. And I replace phi by this, and I get my potential as a function of psi, and you get, after simplification, you get this 1 over 4 alpha (1 minus exponential psi minus psi divided by square root of 3 squared. So this is what you have at the end. This is the StarWitzke model. The StarWitzke model is equivalent to quintessence. Each f of r theory you will consider will be equivalent to some quintessence field with some specific potential. Now the potential depends on the f of r you considered at the beginning. And StarWitzke will be this very specific potential. And the transformation is simple. You know what is the definition of the potential as function of phi. You know what is the relation between phi and psi. And that's it. Then you just do the calculation.
So which term is potential term?
Which term is?
Potential you are talking.
The potential. This one.
Potential term.
Ah, this is this action. This part, it's called quintessence field actually. This is something that people use to for dark energy, etc. And they say that it's the simplest scalar field we can imagine. It's just half kinetic term and potential. So then people started having more complicated things, coupling this, etc. It's the simplest scalar field we can imagine, and it's called quintessence actually. So if I plot this potential, I'm getting this. I'm getting something which does like this. This is my potential. And now we understand why that can produce acceleration. In inflation, it's called slow roll inflation. It means that when the scalar field is large enough, we are somewhere here. So that is my scalar field, which is on top of this potential, and start moving, for example, in this direction. At the beginning, the potential is very, very flat. Actually, you see it here. When psi is very, very large, this exponential is 0, and you get just a constant. So this is this constant here. So the potential is very, very flat, and because of that, the scalar field actually goes very slowly here. When it arrives here, it will fall very fast. But here the scalar field goes very, very slowly. Because it goes very slowly, it doesn't change much in time. So the scalar field is almost constant. And the constant produces acceleration. So the scalar field will go very slowly, produce acceleration, acceleration, acceleration. And when we arrive here, it falls into this potential, start going much faster, changing fast, and then we don't have any more acceleration because it's not anymore a constant. So then we have acceleration, and we can exit the acceleration. And that is the good thing about inflation, because the early acceleration of the universe is a universe which accelerates and then starts slowing down. So that is why this model works very well, because it has exactly the shape of the potential we want. Okay? This is in a Friedman universe. The curvature goes like that. This is the Hubble function, which is a dot over a, and this is h dot. Now, when you start having an acceleration in a specific way, which is that you have that the scale factor goes as an exponential of time, so it goes very fast. This is called the theta spacetime. When you have this, h is a constant. If you do a dot over a, if you call this alpha, it's just alpha, it's a constant. So during the acceleration, h is constant. H dot is 0, so the curvature is constant. Okay? So during that acceleration, r is almost constant. And after that, you get a big change because also this changes. So yes, r follows the same thing than phi in the same picture. During the acceleration, r is more or less constant. And then after that, it changes. Okay, so this is in this way, we can just by hand, without doing calculations, understand why StarWitzke model actually produces an acceleration. Don't know if you have questions, otherwise I will just go a bit faster now, because that was not only what I wanted to do is, okay, we produce an acceleration at early universe or at large scales, etc. What's happening locally? Because we want to make things in such a way that locally the problem, this modification will not bring any kind of complications. So let us see what is happening to the geodesic equations. Okay, so the idea is the following, is that we are now in a new frame where matter is coupled to the scalar field. So when matter is moving, it follows the geodesics of Einstein, but at the same time there is a scalar field which is producing some force on that matter, because the matter is coupled not only to metric, to the geometry, but also to the scalar field. So it feels both at the same time. So how can we do it? The simplest thing is to study what is called the equation of geodesics. That is what is giving us the motion of the matter. So the equation of geodesics, but in the new frame, so means with a bar here. So that is what, in the new frame, with the new metric, the bar metric, we are going to calculate. So we already did all the calculations. We have written that G mu bar is equal to some exponential 1 over 2 square root of 3 psi G mu. Remember that G mu bar was omega, times G mu. Omega is now square root of f prime, and f prime is related to psi in this way. So I just summarize all these steps, and I will call beta just to simplify the notation, this. So this is just exponential minus beta psi g mu nu. Okay, so having this metric, I can calculate what is gamma mu nu rho in the new frame. So we already did this calculation once. So let me just write directly the result. You get gamma mu nu rho, and you get minus beta over 2 delta mu sigma g rho psi minus plus delta mu rho d sigma psi minus g mu psi g rho sigma. So replacing this in the equation of geodesics, I'm getting the standard geodesic equation plus an additional term here, minus beta over 2. I will not write everything. Dx rho d tau, dx sigma d tau equal to 0. So now my geodesic equation, if I look at it in the Einstein frame in some sense, is different. I don't have this equal to 0, but I have some additional terms here. So remember that this is the acceleration of the particle. So if we go back to Newtonian physics, the acceleration is equal to the forces. So these are the forces, this and this. So we have an additional force which is produced, which is going to have an effect. So this is the standard calculation in GR. You go to what is called the Newtonian limit, and you find the gravitational force. So I'm just going to look to space part. So when mu is equal to I, means that I'm looking just to the acceleration of x, y, and z. And I'm considering that the velocity is small. Remember that here we have velocity. Is much smaller than the speed of light. So what does it mean? Is that when I write this term, for example, I'm getting gamma, and the main part will be gamma 0, 0, I, dx 0 d tau, dx 0 d tau. The other terms that I should have, like gamma 0 I or 0 j I, because I have to make the summation of all terms. These are negligible because I have velocity, and velocity in the Newtonian limit is negligible compared to here where I have the speed of light, because this is c times tau. So this is c actually. This is c squared. So all the other terms will be negligible. Only this term is left plus this. And here the same. I take just the 0, 0, which is the only contribution, equal to 0. This is called the Newtonian limit. So you neglect the speed of the particle compared to the speed of light. So doing that, what do you get?
You are considering only time component, no?
Yes.
Space component you are not considering.
No, depending where. Here I'm considering only space component,
Yeah, they are not there.
but in this summation, yes.
Yeah, in that summation.
I'm just considering when rho is equal to 0, sigma is equal to 0, because this is going to be the dominant term. Where every time I have a space term, it's going to be a velocity, and velocity is negligible compared to the speed of light. So I have now a new equation, which is going to be this. And the additional term, which is minus beta over 2. And there are, you take the zero term of it, because I erased it. Where was it? So considering the zero term of it, you get a 2 dy of psi. I mean times c squared, I take c equal to 1. There is no factor 2. So you just consider the formula that I erased, and you take it at rho equal to sigma equal to 0, and you will get that. Okay, so now we are left only with this term here. This is gi sigma, g0, g0, sigma plus twice this minus d sigma g0, 0. Again, we work in the Newtonian limit. In the Newtonian limit, we have that the gravitational field is almost static, so it doesn't change. And this is 1 minus 2 phi, or 1 plus 2 phi. Sorry, minus 1 minus 2 phi. Okay, and this is the gravitational potential. I don't know if it is clear or not. So this is the standard Newtonian limit, how to recover Newtonian limit. So okay, so we get that the acceleration, you have the derivative of minus 1 is nothing, minus minus is plus, the factor 2 goes away, so you have plus dy phi and minus beta over 2 dy psi equal to 0. So then we recover the Newtonian limit. Imagine that you didn't have this. This is acceleration equal to minus dy phi so the acceleration, remember that minus the gradient of the potential is the Newtonian force. This is the Newtonian force divided by the mass. The force is mass times the minus the gradient of the potential. So this is exactly the Newtonian force. We recover the Newtonian equation, which tells us that the acceleration is equal to minus gradient of the gravitational potential, except that we have an additional force here, which comes from the scalar field. That scalar field produces also a force. So the force divided by the mass is equal to beta over 2, the gradient of psi. So this is what we call usually the fifth force, because we have 4 fundamental forces, so that will be the fifth one. So the gradient of the scalar field produces also a force on the particle. So to see it in 2 different pictures. One picture, you're working F of R theory. You have a theory which is much more complicated. It's R plus alpha squared plus etc. Okay. Now, in that picture, it's modified gravity. It's not exactly GR. In GIA, we know exactly the geodesics, etc., and we cover Newton. Here, it's the same thing that you say that you have Newton, but you have an additional force, which is produced by this scalar field, which makes the modification of gravity. So the main thing now, of course, is that we don't like this. This is an additional force. We have never observed that. When you do an experiment in a lab, you don't observe that. You just observe Newtonian force. And this is why yesterday I was talking about all these constraints. There are many constraints in a lab. For example, the Edvosh experiment with distortion balance, etc., where you are measuring, and we went to a distance of 56 micrometer. And up to that distance, we have never measured any deviation from Newtonian gravity. So from where comes this force? That's the difficult part, actually. So, but actually, we will see now, it is solved in this kind of theories. This is why it has what is called a screening mechanism. Okay, so I will skip a bit things. Let me maybe just make it a bit more by hand in order for you to understand, and the calculations will be in the notes. So we have an additional field, an additional scalar field, and produces a force, and that force actually should be observable. That force is exactly what we want to produce, for example, an acceleration of the universe. We are happy with that at large scales. But at small scales, what is happening with it? We don't observe it. So the picture is the following. Remember that, where is my action? So I will remove the bar because now we know, so I don't need to write it all the time, just to simplify a bit the notation. Plus the matter part, which is coupled where beta was minus 1/2 square root of 3. Hope I didn't put some minus sign. Yeah, beta equal to minus. Yes.
So you are taking acceleration 0, so this equal to this?
No. I didn't put acceleration equal to 0.
Then how we can get this f upon m is equal to this?
Yes, no, what I'm saying is that let me multiply this by mass. So I'm getting mass times acceleration is equal to minus mass times the gradient of phi plus mass beta over 2 gradient of psi. Yeah? I'm just writing it with vectors now, not indices. So this is the equation there, I just multiply by mass. What Newton is telling me is that mass times acceleration is equal to the summation of all forces. So the first one is the gravitational force minus m times the gradient of phi, and plus I have a fifth force, an additional force, which is this one.
Okay, so you are just comparing now.
Yeah, so the force divided by the mass is this term here. But actually both are gravitational origin. That scalar field comes from gravity. It's just this conformal transformation, blah, 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 etc. But it's really coming from gravity. But we are just saying that at the end, we don't get exactly Newton, but we get some additional term. And this is why it's modified gravity. But we don't observe it. So we have to be sure that in local experiments, this will disappear, and we get only that. But at large scales, this will dominate maybe and produce an acceleration of the universe. If we have this, we are happy.
Excuse me, sir.
Yes?
At what scale we are considering this additional term?
Yeah. So at which scale this one will be negligible? Yeah. So this is what we are going to see in this mechanism. Actually, I should not talk about scale. This is the mechanism we will see tomorrow, which is called Einstein. In this scale, it's not about scale. It's about the density of matter. And we are going to see that when you are in an environment where the density is very large, like on Earth, this will disappear completely. So if you do an experiment on Earth here, then this term will just disappear. If you go at cosmological scales, where the density of matter is very, very small, the density of matter at the scale of the universe is 10 to minus 29 gram per centimeter cube. There is almost no matter. Then this one will start becoming dominant, actually. So it depends on the density, and this is why it's called the chameleon field, actually. It changes according to the environment.
So density is very low then, and we have connection of potential and density.
Mm-hmm.
That
Yes.
means then the role of potential would be negligible?
No, we will see actually the potential changes because of density. This is what I'm going to show exactly now, actually. The density affects the potential and changes its shape, actually. So as I said, I have this action. And let me just focus on the equation for the scalar field. So I'm making the variation with respect to the scalar field of this action. So I'm getting a d for x square root of minus g. The curvature scalar does not depend on it, so that doesn't matter. So then I am having a minus d mu psi d mu delta psi minus v prime of psi delta psi. And then there is a variation of matter, because matter depends also on the scalar field. So if I am impose now that this is 0, I'm getting the square root of minus g. So sorry, here you have to do an integration by part. So it becomes plus box psi delta psi. So you get box psi minus v prime psi plus delta sm. Oh. Okay. So this is going to be my equation. Okay, so the last part is just to say that this is the variation with respect to g mu and the variation of g mu with respect to psi. That is okay, we can always do it. So let me and divide here by square root of minus g. So this is the equation I have. Now, the energy momentum tensor, I think I never defined it yet, but it's defined in this way. This you can take it as a definition. So this term here is minus 1/2 T mu. Now the G mu depends on the scalar field. I don't have it anymore, I erased it. It was So you have this relation, which is that G mu bar is equal to exponential minus beta psi G mu, which means that G mu is equal to exponential minus beta psi G mu. So the variation of G mu with respect to psi is equal to minus beta, and everything else so means G mu. So this is minus beta G mu. So then I'm getting plus beta over 2 times the trace of it. So my final equation, and this is where we are going to be able to conclude, is that we have an equation which is box psi minus v prime psi and plus beta over 2 t. Equal to 0.
These are your equation of motion.
Yes. But yes, that was the problem of changing notation, is that I confused the bar and the not bar. All this is bar, of course. And I said, because we are not going to confuse them, but I confused them actually, that is a bar. So this is bar here. So let me put back the bars in order to be sure not to confuse them. So this is bar, but the T mu is defined without bar here, because this is the T mu in the original frame. So this here is not this, it's minus square root of g divided minus square root of g bar minus 1/2 of it. There is this term which remains, and you have to put this term in order to get this here. So actually you have a coefficient and now it's correct. But this is something we already calculated. The metric G bar, it's 4 times this. We take the square root, so it's 2 times. Okay, so when we do this divided by this, you get an exponential 2 beta. Okay, so this is my equation now. Questions so far?
So what you will say, this is the equation of motion in modified gravity, or what
Hmm?
equation of motion in
Yes.
modified gravity?
Yeah.
Or
Yes, we see now that actually what I have is the following situation. Let me write what is T mu. This is if I take a perfect fluid. So the trace of this is equal to this, minus density plus 3 times the pressure. Now, in most of the situations, I will neglect the pressure if I consider only dust. So this is just minus the density. This is the dominant thing.
Even it locally, it will not affect the bending of light also. Locally also.
Yes.
We do not go about chameleon, but in the present scenario also, is it like that?
What is bending what? The scalar field?
Yes, this modification will not
Yes.
affect the bending of light.
Yes. It depends where you do the experiment.
In the solar system, of course, in the here actually.
No, if it is here, if the density is large enough, there is no effect at all.
It's trace because it is trace. So
Yes.
it's coupled with the trace.
Yeah. Yeah, no, you are saying so that the radiation is stressless, so it's not coupled to it? Yeah, so it's not coupled to radiation, but it's coupled to matter.
I'm taking radiation.
Yes. No, but you need anyway some, yeah. So imagine that we do our experiment on Earth. The scalar field is also coupled to matter. And we are going to show that because of that, it changes completely and that scalar field is not there anymore. So then if the photon passes, it's like if there is no scalar field. That's the thing. So having the T, let me write it like this. Plus minus beta over 2 exponential 2 beta psi times the density equal to 0. But the interesting thing now is that this, I can write it as a minus some effective potential where the effective potential is the potential, it's a psi, is the original potential plus 1 over 4 exponential 2 beta psi density. If I do that, it's fine. So I have an equation which is what we call a Klein-Gordon equation. So I'm back to a very, very, very standard field. I'm just having the most standard scalar field I can imagine, and that gives me what is called the Klein-Gordon equation. Except that the effective potential depends on the density of matter, actually. So in different environments, if the density is large or if the density is small, the effective potential actually changes. So let me put the picture of it. Let us keep working with the StarWitzke model, for example. The StarWitzke model, I had something like this. And then here it goes like that. That was the original potential we had. But then we need to add this actually exponential terms. So this exponential will bring something it will change, it will be some it will be something like that. So my effective potential will actually look like this. That is my effective potential. Okay? Now, if the density becomes larger, the effective potential becomes like that. So my effective potential changes its shape because of the presence of the density of matter. So the situation is the following. Imagine that the scalar field at some point of time goes here at the minimum, it goes at rest. We know that the scalar field is at the minimum. Here you have V prime in this equation. So what is the V prime? Is more or less V prime of the minimum. I will call this the minimum, which is 0, because we are the minimum, plus V double prime at the minimum times phi psi minus psi min. So my equation here becomes box psi minus V double prime something like that. And this is an equation that we know, where this is interpreted as the mass squared of the scalar field. So what we are saying is that we have a scalar field. That scalar field is massive. Its mass depends on the environment. When I don't have density at all, I will be much more open like this. The second derivative of the potential will be very small. So the scalar field will be very light. Now, when the density is much larger, the potential becomes more like this. The second derivative becomes much larger, so the scalar field becomes more massive. So we have a scalar field which has a mass which depends on the environment, on the density of matter. When the density of matter is large, it becomes heavy. When the density of matter is small, it becomes light. And the point is, when you have a massive field, the massive field brings usually what is called a Yukawa potential, in the sense that the force goes like this, like the scalar field, let's say, divided by the mass squared. When the mass goes large, the force is completely suppressed. When the mass is small, the force becomes actually large. So when we are on Earth here, the scalar field is here, except that that scalar field becomes so heavy, so large, that it actually doesn't affect anything. When we have a massive field, it affects really at very, very, very small distances. Why gravity affects at large scales is because the graviton doesn't have a mass. Why electromagnetism? Okay, there is a screening effect because of charges, but it should be also at large scales because it is massless. When you have a field which is massive, the range of the force is the inverse of the mass. This is the Compton wavelength. So when the mass becomes very large, the range becomes very small, and the scalar field does not interact at large distances. So this is how we are screening the thing. If you keep doing an experiment on Earth, you will never observe that scalar field. That's the philosophy of it. You want to observe that scalar field, you have to go away from the Earth. So then people imagined something which is, let's take a telescope, a spaceship, a small spaceship, and let's go far away from the Earth. So we have the Earth, and we go far away with a very small spaceship, and we do an experiment of free falling or whatever in that spaceship. But now the scalar field around is coupled to very small density of matter. So then we should observe it. That costed a bit too much, so people took some time to do it, but actually they did it. It's called microscope, and the results just came recently, 1 week ago. But this I will talk about it on Saturday, if they say something interesting or not. But the main thing was the following, is to say that if we keep doing experiments on Earth, because the scalar field is so much coupled to all the matter here, we don't feel anything. We are not going to measure it. If we go far away, where there is no matter, that scalar field starts becoming very light, and then it interacts at very large distances and produces all the effects that we want. So this is why it's called a chameleon scalar field. It's a chameleon mechanism. That mechanism is there from scratch. We didn't put it by hand. We are just showing it now. It took some time to show it, but people were working with F of R gravity since decades without knowing about this mechanism. But that mechanism is there, actually. And if you take an F of R theory now, let me just conclude with that. Imagine that you take an F of R theory, something like that. But of course, that depends a lot on the shape of the potential, etc. But anyway, if you take some F of R theory and you start calculating what this will bring at the scale of the solar system, for example. So you study the geodesics in the solar system, the motion of the planets, the advance of the perihelion of Mercury, you calculate all that. And you will see that everything is compatible. But you will not understand it from just simple physics. You will just say that from mathematics it works. But when you go to the other picture, what you see is that really there is one additional degree of freedom, it's one scalar field, but that scalar field is a chameleon. It has a mass which depends on the environment. If you do an experiment near some massive object, you will never observe it. If you do an experiment at large scales, or not large scales, but where the density is low, then you will observe something. So this is the main thing about these fields, about this F of R gravity. I give in the notes some examples, and in order for you to work it out, etc., with all the details. So this is one mechanism. I can already say that actually it doesn't work perfectly. I will give the details of the experiments which have shown that actually it doesn't work very well. It doesn't mean that all F of R gravity is dead, but for maybe the simplest models, it doesn't work. Then you have to cook some F of R action, which is going to be very complicated. Some arctangent, hyperbolic of R, something very ugly. And then maybe it will work, but then you will have to explain why is it like that? Why this action? Why not just taking GR then? I mean, we are happy with GR. Why should we take something so complicated? But it seems to be that the simplest F of R are dead. They don't work, because even if we have this mechanism, it's not enough. Because yeah, the scalar field becomes massive, but how much massive? It has to become very massive. And maybe it's not massive enough, so maybe we should observe it. And people did experiments, and they have never observed it. So they put really strong constraints on it. We will see some of these experiments on Saturday, but it's a mechanism which is nice, but doesn't work perfectly. Tomorrow we will see a second mechanism called Einstein, and it is much stronger and it's still viable. So that's more or less the picture. Questions?
So,
yes?
So the saturation level of the potential, does it increase with the change of that, the way we are changing it for the psi minimum? Is it changing accordingly?
Sorry, say it again.
And I am saying that as psi minimum is changing, the potential curve is also changing. So consequently, the saturation level will also change. Except for the right hand side part.
Yes. No, because, yeah, no, but it becomes just subdominant. When psi is large, you have a constant plus an exponential. So the constant is just negligible, so you just get that. Yes, you kill it completely. But the good thing is that during inflation, there is almost no matter. So this is zero during inflation. So during inflation, you have just this actually. Particles are produced after inflation. So then you have this picture. You can produce inflation. After inflation, you start producing matter, and then you start changing actually the form of the potential. But it's not done only for the model of inflation. It's made mostly for dark energy models, and there are plenty of models in the literature for that. But as I said, at the end, if it becomes really, really ugly, it's much better to work with GR. GR is a beautiful theory, it's simple theory, and it's compatible with all observations. So in that sense, it will be, I mean, why should we take something very complicated? But at some point of time, there was, maybe we can work it out with simple examples, and they will be consistent. It seems not to be consistent. We will see the experiments on Saturday.
You are mentioning about that one can, if you go in the spaceship and you can observe the scalar field, but practically in what manner one can observe or?
For the simplest thing, and this is what they did, is the free fall. So if I take two objects, equivalence principle, with masses which are different, according to GR, etc., according to equivalence principle, they should fall exactly with the same thing. Now the thing is that if we have an additional force, not only the Newtonian force, that additional force might produce something on one object more than the other. So then maybe one will fall faster than the other. And that is the additional force that we have.
Sir, is it like when we will go up like far from the Earth,
Yeah.
the V effective that will decrease because the density will be decreasing. So is it like that additional term will be dominant there?
Yes. Not necessarily dominant, but of the same order of the Newtonian force. So we will get an additional force which is of the same order than the Newtonian force. Most of the time it will be of the same order. It can be dominant, but most of the time it's the same order. So you have the Newtonian force, but you have an additional thing which might make that one force faster than the other. So if you do there an experiment, maybe you can violate equivalence principle. That's the idea actually with these experiments. But there are many other experiments that I will explain which are based on quantum mechanics, because that's the very interesting thing. In quantum mechanics, we have very, very, actually, more precise measurements. In gravity, we don't have so much precision. In quantum mechanics, we have. And people use quantum mechanics to constrain gravity. At least, even if at the end it doesn't give something interesting, the last 10 years were really fantastic in terms of thinking of new ways to test gravity. Because at the end, we test gravity. And people came out with some experiments in a lab using quantum mechanics completely, like interferometer, etc., to test gravity, to test the Newton's law, actually. We have never thought about that before. But thanks to these kind of things, people started cooking some new ideas. We'll see these experiments on Saturday.
So where is this lambda CDM model in this case? Is
The-
it done or automatically accepted?
No,
For dark energy, lambda CDM model is perfectly, I think,
yes,
accepted.
yes.
You did not talk about it.
No. I left this actually. That was part of the motivation originally. The lambda CDM is completely consistent with all observations. Now, it's just at the theoretical level to understand what is lambda and what is CDM. So we know everything about lambda CDM except lambda and except CDM. Lambda is the cosmological constant, and CDM is the cold dark matter. What is dark matter and what is this cosmological constant? So you can link it to vacuum energy, but it has difficulties. And dark matter, you can link it to supersymmetry, but also we don't observe it.
And
So,
also post-title.
yeah?
We are thinking
Yeah.
the viability of present beyond.
Yes.
There. So that also. So okay, we stop here. So anybody who has not written affiliation, because we are printing today the certificate. So if you have not written, it will come without your affiliation.